So, welcome back. This is Kent McVeigh. We're going to talk about pulse crops and production functions. And to do that, I got to talk a little bit about a little math. So, we'll start with a linear equation. So, the general format of a linear equation, if you remember from high school math, is y equals mx plus b. So, where y is the y-axis, m is the slope, and b is the intercept. And I've got another example here. So, this is at y equals 10x minus 5. So the slope is 10. So for every change in x, you get 10 units change in y. And this line intercepts at the minus 5 of the y-axis, right? Where x is 0, y is minus 5. Well, that's one way of writing a general linear equation, but there's also another way. So, and it's called production functions. And so you start off with that, and we're going to solve it. Let me go back here. So what we're using is the intercept of the y, but you could also anchor this equation by using the x as the anchor point. So that's what I'm going to go through in this derivation here. So y equals mx plus b, set y equal to 0 and solve for b. So then 0 is equal to mx plus b, and we'll call this x of 0, just to keep it straight. You can move the mxo on the other side of the equal sign, so negative mx equals b. So solving for x is equal to b divided by minus m. So you can reinsert this b in the original equation. So y equals mx plus b would be the same as y equals mx minus mx0. You can bring the m out because both terms are multiplied by m. So factoring m out, as m is equal to x minus x of 0. So those are equivalent equations, and what it gives you is it gives you the intercept of the x-axis, which is a nice function to have for crop production functions. So to check it, I'll just go through this a little quicker this time. Now to check against the example, x equals b divided by minus m. So you can solve that for x sub 0. And so in our case, b is the intercept minus 5 divided by a negative 10 gives you a plus 1/2. Put that back in the spreadsheet, so x and y, the same ones that we plotted earlier. You can make another column of x minus x sub 0. So x minus half is 0.5. So 1 minus half is 0.5. 2 minus a half is 1.5. And then if you want to solve the second way, they're using this other equation, this equation, you just take this column times the slope. So 0.5 times 10, which was the slope, is 5. 1.5 times 10 is 15. So you get the same values. It just proves that that's the same equation. Now we'll use that equation here in a moment. So this is a study designed for study done at Akron, Colorado on peas, chickpeas, and lentils. So these white circles are risers for irrigation system. So everything grown between these white dots are getting 2 sprinklers. So they get a fully irrigated plot. As you go to the right and go to the left, then you're only getting 1 sprinkler giving water here, and then it's a little farther away, less water here, and actually get outside the length of the sprinkler, this is just going to be a rain fed. So you end up with 4 rates of water, fully irrigated, about half irrigated, a quarter irrigated, and no irrigation or rain fed. The black things are where they went back and they did soil samples to try and normalize their data. So this is the data over a 3-year or 2-year period, I guess 3 years on chickpeas, 2 years on peas and lentils. And you can see this response to, as you add water, yield goes up. That's kind of what we know is true in the semi-arid environment. And here's this equation I derived. So it's the slope times the precip or irrigation and precip total water minus the intercept of the x-axis. So What that tells you, the slope's the same. The slope's the same both ways you write the equation. But for peas, the slope is 8, and the units are kilograms per hectare per millimeter. So I'll change those to pounds per acre per inch in the next chart. But just to compare these three, which one's giving you the highest yield per millimeter of water, per increment of water? A chickpea gives you 10.6, peas gives you 8, and lentils gives you 3.3. So chickpeas are going to respond the most to added water and give you the best yield potential after they start getting yield. But that's where this other value comes in handy, this x sub 0 I called it before. That's the intercept, or you could think of it as the amount of water necessary to get your first increment of yield. The first part of yield is going to come, in this case, 21.5 millimeters, which is almost an inch of water. 25 would be an inch of water. So you have to have about an inch of water before you get any yield, or you're on that line above positive yield for peas. Same thing with lentils. It's about 25 inches, 25.4, before you get any yield. But look at chickpeas. Chickpeas, you have to have 150 or 6 inches of water before you start getting any yield of chickpea. If you take those equations and you put them into a spreadsheet and you calculate as you add water, so this is just hypothetical water from 0 to actually 30 inches of water, and I've changed them from kilograms to pounds, so it's pounds per acre per inch of water. For chickpeas, you have to get 6 inches of water before you get your first increment of yield. It's 49 pounds of chickpeas. Where peas, you're getting yield at 2 inches or just above 1 inch. And so, same thing with lentil. And as a comparison, look at wheat. So wheat, you get 4 inches, you start to get some yield, but it's a much higher response. So you can see quickly you've out yielded any of these pulse crops with wheat when you're getting 12 to 16 inches. If you go all the way up to 30 inches of rainfall, or total water, irrigation plus rainfall, at that point, chickpeas is the best of the pulse crops, but it's less than wheat. But in that range of water you would talk about for dryland production of pulse crops, our average precip here at Southern Ag Research Center is 7.78 inches. From March to July, that's the average of 7, almost not quite 8 inches. March to June is 6.64 inches of rain. So let's say you start with a full profile of water, and let's assume that you can root down 3 feet for all 3 of these, which is probably a stretch for lentil. But let's say you get 3 foot of soil. That's a full profile to start with. That would be on the best soils around 6 inches of water. If you add in another 8, the average, that the max you could expect would be about 14 inches of water. So at that point, peas are still out yielding chickpeas. Even though the yield response for chickpea is greater, it doesn't start yielding until 6 inches. And so peas are going to give you a much better yield overall in our environment than chickpeas are ever probably going to get. You have to get up towards this 30 inches for that to actually switch, probably 25 inches for that to switch, and chickpeas to out yield peas. And lentils are always going to be less, but it's not about the grain pounds so much as is the dollars, and so the dollars comes into play. If you want to look at our initial estimates of water use efficiency for Montana dryland crops, we can use that study from Colorado to kind of give us the numbers for chickpea, peas, and lentils. That's what this data is here. There's other research from Alberta, Canada, which shows similar numbers, and this is again in inches of water, a yield per inch of water. And sometimes they have the minimum water needed and sometimes they don't. But you can see the yield response for chickpeas is around somewhere between 180 to 240. Field pea looks like it's about 180. Lentils in that range. As a comparison, look at grain sorghum. So grain sorghum is a C4 plant, more like corn, and you get a lot more yield per inch of water for those kind of crops than you do for the cool season crops of even spring wheat and barley, or winter wheat and barley. They're more similar to chickpea, these pulse crops. And then the minimum water needed. It's nice to have that number. So we don't really know. Grain sorghum, 10.2 inches. So even fully, and maybe you use 4 to 5 foot of soil water for grain sorghum, it's going to be hard pressed to grow sorghum and get very much yield, even though it's a good response once you start getting that, unless you're irrigating it. And corn's the same way. We don't have any data from Montana. Well, we actually have a little bit of data. So this year I did this study, and Yusuf Muhammad at Eastern Ag Research Center did this study, similar to what they did in Colorado, but instead of using a sprinkler irrigation system, we used drip irrigation, and we could really control the amount of water and make a little bit better experimental design with that. It was a very wet year for both of us, and so that intercept number doesn't make sense. This data is just preliminary, but you can see the yield response around 5.6 is the slope that I saw. And again, this is millimeters, so it's kilograms per hectare per millimeter. Yusuf got around 8.4. That's very comparable to what we saw from Colorado for peas. All we did it was with peas. And all I did was irrigation levels. If we added an inch, 2 inches, and 3 inches as our treatments, he did similar, 0.9, 1.8, and 3.6. So it's basically not an irrigated study, it's a dryland study. We're trying to see what's the response in our environment with peas to added water. And if we would get funding, we tried to get funding through USA Dry Pea and Lentil. They didn't fund us. We're going to go back this year with some data and maybe ask for it again. But if you know anybody that's on the committee for the Pulse Advisory Boards for Montana or for USA Dry Pea and Lentil, a little help would be welcome. So we've got 1 year data. We'll do this again next year, even if we don't get funding, at least on peas, just to get some numbers for our growers here in Montana. Change gears again. We'll talk about herbicide resistance real quick. This is a study. Well, first of all, let me talk about herbicides just in general. This is a graph published in Weed Science 2014 that shows just the timeline of how herbicides came to be registered and used in the United States. The first ones that I can think of knowing, and they were 2,4-D, Banvel, these auxin inhibitors, the ones that make the plants curl and die as you spray them. Those came out in the 50s actually, and were pretty common probably in the 60s and 70s. EPSP synthase inhibitor, that's glyphosate or Roundup. And so this is the timeline of the development of the different herbicides, 30-some different modes of action over time. The most interesting part of this chart is if you look what's happened since 1983 when this last one came out, there's been no development of new herbicides, no new modes of action. So anything that's new, quote new, that you see being sold or being advertised on TV is really just a remix of some of these previously known modes of action. So we don't really see a lot of development of new herbicides. And I'm not sure exactly why the answer to that. I'm not a weed scientist to really know the answer to that, but I think we've developed a resistance to several of these herbicides over time. The glyphosate being the most heard about recently in this state, but I'd say some of the group 2 herbicides have also been pretty notorious for developing herbicide resistance. So the weed scientists here at Southern, Prashant Jha, wanted to do a study with Andrew Kniss at the University of Wyoming to try and look at the shift in herbicide resistance and what plays into it, trying to prove in practice what they kind of know in theory is going on, but it's never really been shown. And then Nevin Lawrence is a researcher that picked this project up at Scotts Bluff the last couple of years. He's actually a previous student of Andrew Kniss at Wyoming. So the study is basically to look at these 3 main effects on the development of herbicide resistance. And I don't think they've got the data on the resistance built yet now, but they do have data that I'll share with you on just the distribution and production of weed seeds and weed biomass. So this chart at the top kind of shows rotation. So they had 4 different rotations. Actually, corn is no rotation, just continuous corn. And the beginning and end of these boxes kind of line up with the kind of the planting date and harvesting date in theory. So you can kind of see the differences in planting date. So rotation 2 is a little more diverse as far as planting date and also harvest date for corn, sugar beet, corn, sugar beet. Rotation 3 is even more diverse, so they're going to add dry beans into this. So corn, dry beans, corn, and then sugar beet. And then rotation 4 was the most diverse at all. So you've got corn, dry beans, winter wheat, which is actually planted the year before the year you harvest it, and sugar beet. So there's 4 rotations. So that's one main effect. Second effect is tillage. So they had a minimum till versus an intensive tillage system. The minimum till is actually no-till. Their intensive tillage is, I think, a rototiller. It's not a plow. It's a very intense disc or disking and then rototilling at the surface. And then herbicides. So the treatments are either all group 2 only type herbicides, which are those ALS type herbicides, like Upbeat, Affinity, Raptor, Resolve Q for corn. Multiple groups, so it would be group 2 plus another group, at least one other. And it varies by crop, of course, so what works in sugar beets won't work in wheat, but you can have a group 2 or group 2 plus another. And so you've got Upbeat plus Roundup for sugar beets, or Affinity plus Husky for wheat. And then the third treatment is no group 2 at all, so no ALS type at all. So it's something other than an ALS for weed control. And basically the data can kind of be summed up in this chart here. For 3 years, at the end of the study, 3 years of the study, you've got results for, this is tillage on this side, intensive tillage on this side. You can see the herbicide treatment here, whether it's a mixture, no group 2 or a group 2, and then you got crop rotation here. The thing that stands out the most from a herbicide standpoint is the group 2s. If you're only using group 2, it has the most number of kochia plants in either tillage system. By having a diversity of herbicide use, you can really drop that total number of seeds produced. Look at this 481 per square meter. That's a tremendous number of plants per square meter that grows in that kind of a corn sugar beet system. As you look at rotation, continuous corn, actually, probably because some of the herbicides that they're using are fairly good control, has better control than a corn sugar beet rotation. That might be mostly because sugar beets are not nearly as competitive as corn. Corn grows 7-8 foot tall, really takes all the sunlight and reduces the amount of sunlight getting down to the ground where seedlings are started and can grow. And actually sugar beets, if you don't control those kochia plants before they can top out above the sugar beet and really dwarf the sugar beet production. Tillage probably drops it in half or at least in half. So a minimum till to an intensive till, adding tillage to the variable really drops the total number of kochia plants in that system. So kochia plants, you have different biotypes depending on, and you're selecting for whatever system you're growing. If you're in a continuous corn system, you're going to select for the ones that are going to survive or the ones that are going to either emerge before corn planting and survive through it, or maybe live through corn planting and make seed at the end after corn harvest. These are different. They added these to different. Well, this is just to show the different pattern of growth for these different crops. So this purple X one came from a kochia plant in Montana. There's some from Kansas, some from New Mexico, some from North Dakota. Some, and this is the cumulative emergence of the total. So look at it by date. So by March 30th, the first part of April, this plant that's from Kansas actually was 50% of it sprouted by the first part of May. whereas this New Mexican one hadn't even emerged. There was no plants had emerged by that point in time. They're the same plant, they've just been grown in different environments, and so you're selecting for different biotypes over time. So that kind of explains why cropping system can have an effect on weed production. So if you're growing barley or wheat, you're planting them really early, probably before there's any emergence of these kochia plants. And so by competition, you don't get near as much emergence of that weed seed coming up. Sugar beet planting time, there's some that have already emerged by the time you plant. So you can do some control ahead of planting time, but there's still 70–80% of the seeds that are in that soil seed bank to come out. Dry beans, on the other extreme, pretty much all of them have emerged by the time you plant dry beans. So you can either use tillage or some type of herbicide control to control that and plant dry beans and have very few kochia plants that survive in that dry bean environment. So that's depending on what your biotype that you have you're dealing with. That's how planting date and crop type makes a difference. And so that's really what the crop rotation impact is on kochia. So when you have a very diverse rotation, you have a lot fewer seedling of kochia that survive. So these green bars are the average, and then this is the standard deviation, this little black bar of the total counts, seedling density, and then seed production. So you can kind of see the one that's really different are these really diverse rotations. The ones that have a lot of kochia plants are the sugar beet corn rotation, just because you've got a lot that come up ahead of time. Continuous corn actually has lower population than a sugar beet corn rotation, and that's probably because the sugar beet just doesn't give much competition to that kochia plant. Corn really crowds it out. And also seed production in a sugar beet rotation, you have seeds that actually make mature seed by the end of that year, which really impacts that next phase, the crop in that next rotation. Whereas after barley harvest, the seeds have not matured, and so you can spray, or you're cutting them off with a combine when you're cutting barley, and you really reduce the total number of seeds going back into the corn system in that corn, dry bean, barley rotation. Take-home message: rotation brings diversity to reduce the total number in the weed seed bank. Rotation can be your friend to really reduce that, and that's true in irrigated production here. It's also true in dryland production. The wheat and barley in that rotation of these irrigated crops makes a big impact both on the front end and the back end. So early planting offers competition against kochia, and early harvest prevents the mature seed production of kochia. Dry bean is late planted. It really gives you control options either by tillage or by herbicide to control those that have emerged before any seed production is made. Sugar beets are the least competitive crop in this rotation in this study. And a diverse crop rotation really reduces reliance on herbicides, and it lowers the risk of developing herbicide resistance, because you're going to use different herbicides because you got different crops. You can use different modes of action. You're not doing the same thing over and over again and selecting for something that can escape that system. Finally, well, not finally, but next on the topic is irrigated malt barley production. And so this graph is just to really show that nitrogen is a significant input for malt barley production. A significant dollar input, 28% of the cost. And you can argue about the numbers. It's going to depend on the rate and what the previous crop was and all those kinds of things, the seed costs. But no matter what you do, it's still going to end up being a quarter or so of the input cost. So it pays to optimize your nitrogen input. So we've done a study here that I've done several years in a row for Miller Coors, looking at optimum nitrogen rates. And so randomized complete block with 4 replications, different varieties over the years: Moravian 69, 115. This 150 is the Bill Coors 100 that they they released or gave it a name, M153. We've done different rates in different years, but they've ranged from 0 to something above what the max needed would be, 0, 40, 80, 120, 160. Plant population is always around 800,000 plants per acre. We've done this under flood, 2 flood events, about 12 hours each. This is the plots. I don't know which year this was, but the way I've been doing these nitrogen studies lately is because nitrogen moves with water in the soil, and so it's typically, if you try and just fertilize the plot, you end up with a border effect where you don't get either an even distribution. So what I've done is put borders between plots. So this row is a plot, there's a border, and this row is a plot, and there's, I think there's 5 rows across. So we only harvest for yield this data from this plot. So these plots are about 15 feet long, about 5 foot wide. You can kind of see where I fertilized from here to here. So we try and get rid of that edge effect. And it's cleaned up our data and made really good data for us to do it that way. And you can see some of the differences as you go down that field. And this is the response to added fertilizer nitrogen, so different varieties. So as you increase nitrogen, yield goes up. As you increase nitrogen, plumps typically go down. Depends on the variety. This Bill Coors 100, which is the M150, actually stayed pretty flat throughout that whole range of nitrogen rates. So as they're selecting for better and better varieties for growing malt barley, that's another reason not to worry so much about not putting on too much nitrogen, is that the plumps, the soil quality, or not soil quality, but the grain quality, malt quality stays up pretty well on these varieties. So the regression analysis I've used for this is just a curvilinear fit, ax squared plus bx plus c, where grain yield is y, or the y-axis, and a, b, and c are fitted parameters, and we're going to shoot to compare them all at the 95% of the maximum level. And so those are the fitted parameters. You can see the fits of the curves are really good fits, and so it's good data. If you go through all that math, you can figure out that the total pounds of nitrogen needed per bushel for that 95% yield is 1.14 in 2014, 1.3 in 2015. We did 2 years in a row where there was up in the 1.3s, and we thought this 2017 will have so we kind of stretched it up, thinking that maybe these new varieties were needing more nitrogen, and it actually came back in at 2 different locations, 101 and 1.04, and in the end, the average is about 1.16, which is about what MSU's been recommending for years for nitrogen recommendation for malt barley production. Plump numbers are good. Proteins are staying low, even at these optimum levels. We're seeing percent protein that's not at a level that would be rejected. This 2015 might be pushing the limit there. And the yield levels are good. I mean, we had 160 bushel barley in 2017 at one location, 140, the average almost 140 bushel. So this is, I feel pretty confident in recommending 1.16 pounds or 1.1 to 1.2 pounds of nitrogen per bushel of yield goal, and know you're going to stay good protein, good plump, and good yield potential. And if you go back to this graph here, shorting your nitrogen by just 25, 30 pounds really impacts yield potential. So there's no reason to really do that if the variety you're growing has got already built into it a potential to keep protein low and to keep plumps high. An example calculation then for doing this is, let's say your soil test came back and you had 18 pounds of nitrate in the 12-inch depth, 10 in the 12 to 24, and 12 in the 24 to 48. That totals 40 pounds of nitrate nitrogen. A yield goal 130 bushel. 130 bushel times 1.16 would be 151. Minus this 40-pound credit would mean you'd want to fertilize that with 111 pounds of nitrogen per acre. I, in this study, have used all the nitrogen that's available in the 24 to 48-inch depth. I know Clayton Jones and our recommendation from MSU only gives half credit for that. So instead of doing 12, you might use 6. that might increase this 111 to 117, but it's not a big number change. We've also done seeding rate studies with Miller Coors, looking at different years and different varieties at 2 locations here in the southern part of the state. Seed rates from 400,000 to 1.2 million. I know that Bush Ag is usually recommended about 1 million. I think Miller Coors recommends 750,000. If you look at yield from 400,000 to 1.2 million, there's no significant difference in yield. It's the same yield no matter what the population is. It just shows that this barley can tiller out and make up for a low population. So even if you only got half a stand, I'm fairly confident, as long as it's uniform across that field, at least a half a stand, your yield should not be impacted by that. We're still recommending 750 to 800,000 plants per acre because you don't want to just depend on tillering to fill that in. But same thing at Fromberg. So calculating seed rates, the desired plants per acre, divided the number you probably are going to be searching for is the seeds per pound. And so that number you need to get from a lab. That'll come on the label, the percent germ and the percent stand is probably what you feel like your seeding system is giving you. You know, if it's a 90% of what you plant is going to come up, then you use 0.9. But this seed weight for barley is typically around 12,000 seeds per pound. So depending on the seed size, it might vary from 10 to 12,000. 77 pounds per acre for that 750,000 plants per acre seed rate. So the last topic I had was on micronutrients, and I just brought this down to zinc because we've looked at both zinc and boron, but we really haven't seen much of a response to boron anywhere. So if you look at the Montana State's table for micronutrient test value, if you have your soil test back from a field and you've got zinc levels below 0.5, you're probably in that value, that range that you might see a response to added zinc. Same thing with these other micronutrients, iron. There's a minimum number. So if you're below that number for your soil test, there's a chance that you might see a response. Now, typically, it doesn't take a lot, and we did this study as a foliar application. Micronutrients are not normally added in our dryland production systems, but there is a push to look at zinc across the state. So we did this study 2 years in a row. This is 2017 results, and we did it at 4 locations. And this is a soil test value from these locations, and you can look at zinc. Actually, we're all testing above that level that you would expect a response, and we thought boron might see a response. And so we actually included boron in our study, but I guess, I'm sorry, here's the zinc. 0.4, 1.1, 0.4. We had one location here on station that was in that responsive range. This is a site from Broadview where we did this. So we're doing it on farm, and you can see where this is actually Keith Schott's farm, and we found some uniform areas. This was a rep here, and there's 4 reps across there. So we spray on, this is at Fort Smith. Same thing, and the color-coded flags are so we can keep track of each different micronutrient product we put on. And so we had a little hand cart with a spray boom on it, and we're spraying, I think it's 8 foot wide, and we come back with a plot combine and do a 5 foot wide swath through the middle. So we're overspraying, and then our plots are 10 feet apart, so we don't have to worry about cross-contaminating one plot with the next. But it's randomized complete block design. Source was zinc sulfate from Alpha Chemicals. I'm not going to talk about the boron. The zinc treatment was applied at 0, 0.3, 0.6, 0.9, 1.2, and 1.5 pounds per acre as a foliar application at joining stage. I won't talk about the other 2. That's the plot size. Applied 14 gallons per acre at joining stage, harvested with a small plot combine. So here's the grain yield for this foliar application of zinc. And if you look, this is bushels per acre. There's actually the p-value has to be 0.05 or lower for it to be a significant response. There's really no difference in yield at any one of these locations to applications of zinc. So we didn't see a response, and the one that we thought, I guess it was Huntley, was the lowest. It really, you try and argue that 91 is versus 98 is different, but actually the first increment of zinc at 99 is just the noise in the data. So, but if you look at the wheat grain zinc content, so we took samples from the grain and sent it off to a lab and had them analyze it for zinc. We can see in actually all locations, I think all locations, see this p-value, I guess 3 out of 4 locations, zinc content went up from 15 part per million up to 23 part per million at Camp 4, 19 to 25 at Hysham and Huntley, 25 to 31. I think the recommended for human diet is around 30 part per million zinc. So we're just above that here at Broadview. We're kind of in the ballpark, just a little bit below on a couple of them. So the story is that we can actually get zinc into the grain, but we're not seeing it as a yield benefit. So the incentive for a producer to put this on that's not going to get paid back for doing that is pretty low. So we did 2 years of this on about 10 locations total and never saw a positive grain yield response to boron, zinc, or this micro 500 that we tested. So I'm not a big fan of doing micronutrient studies or recommended micronutrients, although we're going to do one more study this next year on winter wheat. So we'll see what that does. With that, I'm done. I hope you enjoyed this presentation. And if you have any questions, give me a call or send me an email, and I'd be glad to talk to you about it. Thank you very much.